last lesson, we looked at matrices as kind of a shortcut to solve systems of equations, but they can also be used in many other ways, particularly in business, social sciences, natural sciences, and so forth. In this section, we're going to be looking at some ways to combine matrices so they can be used in those fields. So, the Easy Life company manufactures sofas and armchairs in 3 models, A, B, and C. The company also has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, 5 Model C sofas, 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. Organize the information in a table and then create a matrix based on the table. So I'm going to make a table, and across the top I'm going to list Model A, B, and C. And over here I'm going to have C for chairs. Well, let's do sofas first since they did. So sofas first. And then chairs. And we're going to fill in this table with the information that was given. Okay, so we said 10 Model A sofas. So A sofa is 10. 12 Model B sofas. And 5 Model C sofas. And then for chairs, 15 Model A chairs. 20 Model B chairs. And 8 Model C chairs. So there's a table that we might make. And we're asked now to put this information also in a matrix. So I'm going to make a matrix and just copy the information. 10, 12, and 5, 15, 20, and 8. So there's my matrix, and you can practice doing the same thing in checkpoint 1. There are some standard practices we use with matrices so that we know that we're all talking about the same thing. In checkpoint 1, you constructed a matrix that had the same information as in example 1, but arranged just a little bit differently. To make sure that we coordinate and do things the same way, let's look at some basic rules for matrices. A matrix has dimensions, which tells us how many rows and how many columns. And we always write the dimensions, rows first and then columns. A row is horizontal and a column is vertical, just like the column on a building is vertical. So rows by columns, that's how we express dimensions. So if I had this matrix, I would call this a 3 by 2 matrix because it has 3 rows and 2 columns. Okay, sometimes we talk about a row matrix, which has 1 row only, and a column matrix has 1 column only we also have a square matrix. Which is the same number of rows and columns. Okay, so just some basic definitions. Square matrix, row matrix, column matrix, and dimensions are R by C. So pause your video now and work on checkpoints 2 and 3. Matrices can be added and subtracted if they are the same dimensions. And we add and subtract matrices simply by adding or subtracting the corresponding elements in each. For instance, if I had 5, -6, 8, 9 plus -4, 6, 8, -3, I could add those by adding 5 and -4, so that would be 1. -6 and +6 would give me 0. 8 and 8 is 16, and 9 and -3 would be 6. If I had these two matrices, I can see this is a 2 by 2 matrix, this is a 2 by 3 matrix, and we cannot add because there are different dimensions. Pause the video now and work on checkpoint 4. Let's look at an example of where we can use matrix addition in a business setting. The September shipments of the 3 models of sofas and chairs from the Easy Life Company to New York, San Francisco, and Chicago warehouses are given respectively in matrices N, S, and C. So you can see I can name my matrices with any letter, and the N, S, and C help me understand that N goes to New York, S goes to San Francisco, C goes to Chicago. So this is matrix N. And in our first example, they sent the same amount to each warehouse, but in this one, they're sending different amounts. And the question is, what was the total amount that was shipped to the 3 warehouses in September? To get this, I'm simply going to add 45 plus 30 plus 22, and I get 97 here. 35 and 32 and 25 gives me 92, and then the rest of the matrix is 86, 139, 121, and 100. Okay, and you may be thinking, well, that's nice, but kind of tedious, and couldn't I get a computer to do that? And these days, most certainly you would use a computer to help you maintain track of inventory, but this is how it would be set up inside the computer. Always good to know how the computer works to understand, so that you know whether or not the data from the computer can be trusted. So let's pause the video now and work on checkpoint 5. Here's another example from real life. A drug company is testing 200 patients to see if Pain Off, a new headache medicine, is effective. Half the patients receive Pain Off and half receive a placebo. The data on the first 50 patients is summarized in this matrix. This matrix has 2 columns, depending on whether the patient experienced pain relief or not, and the rows represent whether or not the patient actually received any medication. It's well known that a lot of times when we take a medication for something, the anticipation that the medication is going to correct the problem actually helps correct the problem even if the medication is not effective. So it's always important with a drug trial to have a placebo or something that is not going to affect the condition, to see if the patient can affect the condition by thinking they're getting some medication. So here's our matrix. For this situation. Okay, and this was a pretty small group of patients, only 50. And as with any drug trial, we would never base our results on only 50 patients. So we repeated this drug trial 3 additional times. And with the same rows and columns, this is what we got. And so now I want to combine all of these matrices to find out overall what was the effectiveness of this medication. So I'm going to add these all together, and my result is that so for this particular medication, for the people who took it, 85% got relief. For the people who got the placebo, we had some that got relief, 27%. But this seems to give evidence that the medication is actually doing something. So pause the video now and work on checkpoint 6. Earlier I said that matrices could be subtracted and they follow the same rules as for matrix addition. Let's look at some examples. Okay, to subtract these matrices, I just subtract these numbers from these numbers. Some of you might find it a little bit easier if you change this to addition and then just change all the signs inside the matrix. Especially when we're subtracting negative numbers, sometimes it gets confusing. So I like to do this, and I get a result of three, -1 and 3, and here -1, 6, and 3. Let's look at a different matrix, this time a row matrix. And again, I'm going to change this sign, this sign, this sign, and this sign. And I have 8 minus 3 gives me 5. 6 minus 5 is 1. And -4 plus 8 would be 4. And lastly, we'll do a square matrix. Minus a small column matrix. But just as with addition, if the matrices do not match in dimensions, then subtraction is not possible. Pause the video now and work on checkpoint 7. We're going to return to the Easy Life Furniture Company for a real-life example of how we might use matrix subtraction for inventory control. It says during September, the Chicago warehouse of the Easy Life Company shipped out the following numbers of each model where the entries in the matrix have the same meaning as given earlier. So they're calling this matrix K. Got 5, 10, and 8, 11, 14, and 15. This is things that went out. Okay, our earlier matrix was things that came in. It says, what was the Chicago warehouse's inventory at the end of September, taking into account only the number of items received and sent out that month? So we need to go back to our other example to get that Chicago matrix. this was 38. I'm going to take this matrix, subtract this one, and my result is C minus K Okay, so this is inventory control using matrix subtraction. We'll cover matrix multiplication in another section, but we can also do an operation called scalar multiplication. In scalar multiplication, every element in a matrix is multiplied by the same number, a scalar. A scalar is not a matrix, it's just a number that we can use to manipulate a matrix. Let's look at an example. I write my scalar outside the matrix, not in brackets because it's not a matrix. And then I simply multiply. -3 times 2 is going to give me -6. -3 times -5, positive 15. -3, -21, -12, and positive 18. And that's scalar multiplication. Pause your video now and work on checkpoint 8. The last thing we're going to look at in this section is finding the additive inverse of a matrix. Just as the additive inverse of a number is a number that we combine with it to get 0, the additive inverse of a matrix is a matrix that we can add to the original to get a matrix that has all zeros in it. For instance, if matrix A looks like this, the additive inverse of matrix A would be and if matrix B was this, then negative B would be like that. When we add a matrix to its additive inverse, we get a matrix where all the elements are 0, and we call this a zero matrix. Your textbook gives you several properties of matrices that are very similar to the properties of real numbers. I would encourage you to consult those as you work through problems dealing with matrices. This concludes this lesson. Go ahead and work on checkpoint 9 and then continue on to your homework assignment.